Okay guys, so in this video we're getting into chapter 11. We're learning about the chi-square distribution. So it's a new distribution and there are a variety of tests we can use with the distribution. It's this guy down here. What we are going to be looking at today is known as the goodness of fit test. And so this is labeled as 11.2 in the homework, all right? In the homework and on the syllabus. Again, our notes kind of take what was in 11.1 and 11.2 and combine them into one here. So we're going to be introduced to the chi-square distribution, and then the first test we're going to learn about doing is the goodness of fit test. Okay, and that'll be it for this video. So again, we've learned about normal distributions. We've learned about t-distributions. Now we're going to learn about chi-square distributions, okay? And I mean, we've learned about other distributions as well, but those have been the most, normal and t have been the ones we've been dealing with the most lately. So let's learn about this chi-square distribution and see what it can do for us. It can do some neat little things. So one of the main things we can do with it is it allows us to be able to see if an observed distribution fits an expected distribution. Okay, so do our observed frequency counts of a categorical variable fit a particular distribution? So hence kind of the name goodness of fit test, which we'll see. Here's the scenario. Here's this idea. It says that M&M's claims that each package of M&M's should contain 24% blue, 14% brown, 16% green, 20% orange, 13% red, and 13% yellow M&Ms. All right. In other words, M&M's claims that they know the spread of the colors of M&M's, or what it should be in each bag. Okay. So what this goodness of fit test will do is it will allow us to basically take a bag of M&M's and see if by sampling some M&M's can we determine whether or not that statement is correct. So does the distribution we observe, what comes out of our bag of M&M's, match the distribution that is expected, which is what is claimed by the M&M's factory? Okay, so it's a really easy test statistic to calculate, and it's an easy test to do, and there's 5 steps that are extremely similar to what we do with hypothesis testing and that we've looked at in chapter 9 and 10. So let's go through all that. They lay out some notation here. First of all, we're going to use the letter O. That's going to represent the observed frequency from our sample. So if in a bag of M&Ms we found 15 of them were orange, then that observed value, O, would be 15. E represents what we expect, so that's like what is claimed by, in this case, like the M&M's company. They claim that 20% of their M&Ms in the bag should be orange. K is going to represent the number of categories we have. So in the case of the M&Ms, it would be the number of colors we have. Okay, so the number of colors of M&Ms we have. Okay, and then chi-squared is the test statistic. We've had a t-test statistic or a z-test statistic. This is chi-squared. And when you draw the symbol chi, try not to just draw an x, even though it looks like an x. It's sort of got like a straight bar and then a fancy bar. All right, if you can kind of see that. So that's technically how we should try to draw chi, as opposed to just plain old x. Sorry, I'm looking for my charger. So here is the test statistic. This is how it's calculated, okay? And again, finding a test statistic is nothing new to us. I'm going to erase it, but if you just recall, if I wanted a z-test statistic, isn't it usually what we observe minus what the claim is over the standard deviation, right? Similar for t, and the only thing that changes really is between means and proportions. It changes how you calculate standard deviation. But we've looked at test statistics before, and then I take that value and go find a p-value. And based on the size of that p-value, I reject the null or I fail to reject the null. That's exactly what's going to happen here, except this is not our test statistic. This is our test statistic. Okay, so if you remember, this symbol right here means to add everything up, right? The summation symbol means we add. And so what you end up doing is for every category, like so for each color of M&M, I would take what I observed from my sample minus what is expected from my sample. I square that so that basically I always get a positive quantity, because if you know E was bigger than O, then this would come out negative. If you start adding a bunch of positive and negative numbers, you can get them to cancel out. So that's something we did way back in learning about standard deviation in Chapter 2. To make sure this stuff is positive, we just square it. So anyways, I take the number of, let's say, blue M&Ms I observe minus the number of blue M&Ms I should have. I square it and I divide by the number of blue M&Ms I should have. And then I add up all of those. So we will add a contribution, which is just one of these things, for each color. Each one is known as the contribution, and together they all add up to give you the chi-squared test statistic, which I can then pull up a chi-squared table. It's on those stat tables that you guys have already posted on Canvas, or you could consult Statcrunch and it can run it for you. So anyways, what it does is, let's just kind of read through here. It says that the chi-squared test statistic measures how far each observation is from the expected frequency. So it's a measurement of how off we are, basically, from what we observe in our bag of M&Ms compared to what is claimed about our bag of M&Ms. Chi-squared is always positive or 0, and you could see that because we're squaring this thing, right? So I'm always going to have positive values. And the larger the number, the farther we are from what we expect, okay? So the larger chi-squared turns out to be, right? Once I start adding all these up for every color, it increases in size because you have more and more contributions, one for each color. Well, the larger that number gets, the further off we are from what we would expect. Okay? Because if what we observe is close to what we expect, then wouldn't this be a small number? If what you observe is pretty much what you expect, then their difference would be almost 0, which means the square of it would be almost 0, which means you wouldn't be adding anything. You'd be adding a bunch of zeros or small numbers. It's when they're really far off, like the observed value is a lot more or less than what we expect, then this becomes a very large number, and then consequently the sum gets larger and larger. All right, so again, the larger chi-squared is, the more off we are. So, and then here, how far is too far? Well, that's what alpha determines, right? When you do a hypothesis test, and here we're just going to do a different type of test, but it's going to be very similar. We are going to pick an alpha value, which is basically our tolerance, and we're going to say, okay, this is as far as we'll expect or accept, or as low a probability as that we are going to accept having the data we do have based on what it was claimed. Okay. So here's what it looks like if you were to graph out the chi-squared distribution. It's skewed right, so that's different, right? We're used to the normal distribution and the t-distribution, which are symmetric. This is right skewed. It's always greater than 0, so 0 is here off to the left, right? Or it could be equal to 0, but it's always positive, so it only exists to the right of 0. These are all positive chi-squared values. Much like the t-distribution, to read the probabilities off of here, you're going to need to look up the degrees of freedom, and it's 1 less than the number of categories you have, right? K is the number of categories you have. Okay. And the area right here would be the probability of getting that area, right? This area right here is our p-value. because ultimately we're going to try and find the probability of getting the observation we did or something more extreme, meaning even further away from what was expected. Okay? So it's going to feel very similar. Let's take a look at the next page. I think for this video they just kind of walk through one big example and then they get into a new use for chi-squared. That'll be the next video. So for here we're just going to run with this M&M idea, and this is the goodness of fit test. Okay, the chi-squared goodness of fit test. All right. So we're going back to that M&M question. M&Ms makes a claim about the percentages of each color in their bag of M&Ms. And we are going to see if our sample of M&Ms fits that model. Or is there reason to believe that the M&Ms company may be wrong and that actually they have more blues, or or it's simply not what they claim. All right. So they've actually already worked out the steps for us. So let's just make sure we are aware of them. Step 1 is the same as it always is. State your hypothesis, and I would in here and state alpha. All right, so here is our null hypothesis. Again, what was claimed on the original problem. Let me go back. They're working off this example here, okay, the very first example written. M&M's claims that 24% of their M&Ms are blue, 14% brown, 16% green, 20% orange, 13% red, and 13% yellow. So that is the null hypothesis, right? The null hypothesis is that here is what M&M's claims. The proportion that are blue, 0.24, proportion green, proportion red, and so forth. Okay, that is the null baseline hypothesis, the original claim. Now the alternative to that is that at least one of these is wrong. Okay, so our alternative is not going to be like, well, there's more blue than what they claim. If you wanted to do that, that would actually just be like a one sample test. You could just only focus on blues and ignore the rest of the colors, and you could test whether or not there's 24% blue or more than that. That's just a one proportion test. So that's back in chapter 9.3. If we're going to look at all of the categories, all of the colors, and we want to see if basically M&M's is correct or if they're not correct. So they would be not correct if at least one of those things is not what they claim. They don't all have to be wrong, but if one of them is not what they claim, then they are not correct. All right, and we hope that our hypothesis test would show us that. Okay, so again, there's step 1. Same as it is. State the null and alternative hypothesis, and let's let alpha be good old 0.05. Step 2, same as it always is. Name the test. I'm going to do the steps in green so they hopefully stand out. Name the test. All right, so again, this is known as the chi-squared goodness of fit test. So sometimes you'll just see it written chi-squared GOF, goodness of fit. Okay. Everyone's favorite step, number 3, is check the requirements to make sure you're doing good stats. Well, it's still independent, random, and large. It's just the large enough is slightly different. So independent, we still probably are going to use the 5% rule. That's the same. Random, we hope to have random data. Nothing new there. Now the large enough is a little different, right? This is new. But we're used to that because doesn't large enough, doesn't that differ whether or not we're talking about means versus proportions anyways, right? The large enough case, it really depends on what you're analyzing. All right, so if it was means, we need more than 30, right, in our sample, 30 or more. If it's proportions, we need the number of success and fails to be at least 10. If it is a chi-squared distribution, the expected frequency count has to be at least 5 from each category. Okay, so in other words, you have to have a big enough sample so that you would expect to get 5 of each color of M&Ms. Okay. So I couldn't sample only 10 M&Ms because then there's no way to have a total of 5 of each of these. I mean, the bare minimum would be 30, but I even need more than that because I only expect 13% of mine to be yellow. So I have to get a big enough number so that 13% of that number is at least 5, right? I got to expect at least 5 from each color. Now, when you're verifying this step, this last one, it actually kind of makes sense to do, it's weird, but it almost makes sense to just jump to step 4 and then use your results from step 4 to kind of verify that, yeah, we are indeed large enough. You'll see why when we get here, but you want the expected frequency count to be at least 5, you have to find these. And that is something that we do in step 4. So especially if you were going to use like Statcrunch or something like that, then I would just run it through Statcrunch. And one of the things Statcrunch will tell you is what was the expected amount of each category. And then so sort of after the fact, I can go ahead and just sort of verify, yeah, we were good. So you could move on to step 4 if you're doing Statcrunch, or if you're not, then you could just feel free to do it right now. Okay, you've got to find these expected counts. So let's just hypothetically suppose that our bag has 200 M&Ms in it. And so what they've done is they've reminded us of each of these percentages. There should be 24% blue, 16% green, 13% red, and so forth, right? These are the claimed percentages. Claimed or expected. All right, so what is the expected number of blue M&Ms we should get then if we're looking at 200? Well, if I've got 200 M&Ms and 24% of them are blue, the expected blue, so they use E sub blue, E for expected, you simply take the number of M&Ms you have times the percentage that should be blue, and that'll tell you how many you expect. Now, I need, in order for the large enough category to be met, or requirement, I need 5 of each color at least. So we've got enough blues, we're good there. But how about the rest of them? Let's kind of start writing them out. So I also need to find the expected number of brown. Well, that's the number of M&Ms times the proportion that are supposed to be brown. So that's 200 M&Ms times 0.14. That's 28. Well, that's enough. And I need to do this for all of these. And so I'll do them real quick. Green, it'd be N times the percentage or the proportion that are green. So 200 M&Ms we're looking at, and 16% are supposed to be green. That's 32 of them. So let me just write the rest of these out really fast. Orange would be 200 M&Ms times the percentage that should be orange, so that would be 40. The expected number of red would be 200 M&Ms times the proportion that are supposed to be red. That would be 26. And the expected number of yellow, same deal, 200 M&Ms, 13% are supposed to be yellow, another 26. So all of these are greater than 5. So let me just make that note. We are large enough. All right. So the large enough requirement is met, and we are going to need all these numbers for when it comes to actually doing step 4 on the next page. Okay. All right, so again, the 5 steps we've done so far, or the 3 steps, is step 1, we have named, stated the null and alternative hypothesis and our level of significance. We have named the test, and we have checked that we're doing good statistics. We checked IRL. Again, it's just there's a new large enough requirement for this particular test statistic. Okay, let's look at step 4. So here is again where you do the thing, right? Step 4 is where you actually find the test statistic and then find the p-value. All right. So what they have done is they just made this up. So again, this is what we expected. These were the numbers that we should have just found under the expected. We expected 48 blue and 28 brown and 32 green and so forth. So this is what we should have just verified or found on the last page. And it turns out this is what was actually observed. In their bag of 200 M&Ms, they actually got 55 blue ones when they were supposed to have only 48. They found 20 brown ones when they were supposed to have 28, and so forth. So you have what we expect out of there and what we actually have in that bag of M&Ms. So now what I need to do is, again, I want to build this test statistic. All right, the chi-squared test statistic, and it's the sum. I have to add up the contribution from each of these colors, okay? So we need to add up the contributions for each color. So the contribution for, let's say, for blue. Again, this is the general form of your contribution right there. Each one of those is my contribution. So I'm going to take what I observed. I observed 55 blue ones. That's what they told me were in the bag. I expected only 48 blue ones. I got to square that and divide by what I expected, 48. And let's see, that comes out to 55 minus 48. That comes out to 1.02. Let's just go to 2 decimals here. So there's the first contribution. And so if I'm going to find chi-squared now, what I'm going to do is I'm going to take all these and say, okay, well then the chi-squared test statistic is going to be the contribution from blue plus, now I need the contribution from the next color, so how about from brown? All right, so what I observed was 20. What I expected was 28. Square it and divide by what you expected. That's 2.29 if I round. So that is the contribution from the brown M&Ms. And then on to the green, the orange, the red, and so on. I'm going to go ahead and pause it for you to shorten the video, and I'll write all these out and then I'll start it again, okay? Hold on one sec. Okay, so I added in the rest of the contributions and then I would add them up. So here was the contribution for blue and brown, and then there's green's contribution and orange's contribution, red's contribution, and yellow's contribution. And if I added all those things correctly, I got about 8.26 for my test statistic. All right. So what we're looking at is we're looking at a chi-squared distribution. I've got some test statistic at 8.26, and I'm going to be interested in the area to the right of that thing, right? That right there is going to be the p-value that I look for. Okay, so I'm going to consult my chi-squared table and try and figure that out. So again, we're still on step 4. Remember, it's only half done. First is find the test statistic, then find the p-value. And when I run this on Statcrunch, I bet we don't get this exact answer. I know we won't, but it should be close. I rounded everything to 2 decimals, so had I gone a little further, this could definitely be a little different, but probably good enough for our purposes. Okay, well, when it comes time to find the p-value, again, this is what we're trying to figure out right there, is what is this area? That's my p-value. okay? I mentioned earlier, and we're going to see real quick on the table, that you have to know what your degrees of freedom are, right? Chi-squared, like the t-distribution, is dependent on our degrees of freedom. Oh, it looks like my value should be 8.42, not 8.26. So either I miscalculated a little, or maybe this is the more exact answer by taking more decimals. I'm just going to go ahead and change it to what my numbers are. I want to know what's the probability that chi-squared is to the right of 8.26 is what I got. Well, let's look at this on the table and get an idea here. So let me go find our stats tables. So I already scrolled down to, it's at the, for your stats tables, again, you have two z tables, a t table, and then at the bottom is your chi-squared distribution table, okay? So the first thing is I got to settle on what degrees of freedom do I have. So there were 6 different colors of M&Ms, right? So if that means that K is 6, so your degrees of freedom is always one less than that. So I have 5 degrees of freedom in this problem. Okay, so I'm going to find 5 degrees of freedom. Now, what I need to do is I need to look at these scores. So again, this works very similar to a t-table. Find your degrees of freedom, find the score in the middle, and your areas to the right of that score are up top, right? So this area to the right is all these. It reads exactly like the t-table. Remember, the z-table puts the areas in the middle here, not for the t and the chi-squared. The scores are in the middle, and the areas are up here at top. So I was looking for the probability of getting a chi-squared value greater than 8.26, I think was what I found. So let me get as close as I can to 8.26. So there's 6.63. It would be like right around here, wouldn't it? It'd be somewhere in between 8.1 and 9.2, but it would be pretty darn close to this 8.2. So therefore, I can kind of figure out that my area would be in between 0.15 and 0.10, but closer to 0.15. So I don't know exactly what it is, but I can safely say that it's in between 10% and 15%, and it's closer to 15. So at the very least, I could say this is greater than 0.10. It's definitely bigger than 0.10, right? Because it's closer to 0.15. That's all I need. All I need to know is how does it compare to alpha, so therefore I could reject the null or not reject the null. So I don't need to know exactly what it is, but I mean, I would guess that it's around like 14% or something, right? Because it's in between 10 and 15, but it's definitely closer to 15. So it's probably around 14%, whatever. It's bigger than our alpha, so that will tell us what we need to do with the null hypothesis. So let's go sum that up and write our conclusion. Let's go back to the notes here. This page. Next one. Next one. Okay, so we've got our p-value here. I'm just going to say that the p-value is greater than 0.10. I don't know exactly what it is. We will once we roll it through Statcrunch. Oh, I guess this is what we should find. 13.4%. So that's pretty close to what we guessed, like a 14%. All right, and they went ahead and did the conclusion for us. They really took care of us on this one. So the last step, again, step 5 is always write up the summary. What is your conclusion? And so since our p-value was greater than alpha, that's what I would say, since our p-value is greater than alpha, right? And again, alpha is the bare minimum likelihood we are willing to tolerate. What this represents is this 10% represents the probability of me getting this batch of M&Ms I did when we expected that many M&Ms. Okay, so again, that's what the p-value represents. We expected this many M&Ms of each color. This is what we got of each color. So the probability of getting that color distribution is just barely over 10%. All right, so it's not likely to happen, but it's not too low of a probability that it causes us, you know, to want to reject the null. It's unlikely to happen because it's kind of low, but it's not low enough to make us think that M&M's is wrong. In other words, we do not reject the null. We fail to reject. All right, so if we do not reject the null, let me go back to the null, it means that we just assume that we say, well, seems like that's okay. We do not go with the alternative that states that one of these is off. It just seems that M&M's knows what they're talking about, and the data suggests that, yeah, that is, even though we got something a little different, it wasn't extreme enough difference to make us think that M&M's has it wrong. They must be having it right, at least by our example, from our sample. So we have insufficient evidence to show that the color distribution of M&M's is different than what they claim. Okay, the data does not suggest the difference is something other than what M&M's claim, or the distribution, I'm sorry. Okay. So the chi-squared is a neat test. Like I said, it can be used for a whole variety of things, and we'll see some other uses of it in a second. But or I mean in another video. But the goodness of fit test is pretty cool. You can imagine it can extend well beyond M&Ms, right? But I mean, say you're talking about a population at a sporting event, you know, and the claim is that, you know, 10% of the people are between 20 and 25, and 30% are between 25 and 30, and so on. They give a breakdown of people's age. If that's the claim, you can test that claim by taking a sample. Take a sample of 100 people or whatever's necessary to meet the requirements. And from our sample, you would be able to determine if that claim is true, or if the data suggests that that original claim is off, and maybe there's a higher or lower percentage of a particular age category. Right? So the goodness of fit test is pretty neat. Okay, everybody, that's it for this one, and we'll have another Chapter 11 video coming for you shortly. And then that's it, and then we're nearly done with this course. Good job, hang in there. I logged off, and then I realized that I was going to show you how to do this on Statcrunch. So let me show you how to do that real quick. I'm just going to take this data right here, the observed number of M&Ms we found and the expected number of M&Ms we were hoping to get. So let me run to Statcrunch. So in here I'm going to put what I observed and what I expected. So what I observed, I'm just going to put down in order from what the table has. 55 blues, 20 brown, 35 green, 49 orange, 18 red, and 23 yellow. That's what I observed. And I'm going to put the expected next to them. Make sure you're going with the same colors. So blue, 28, that was 32 expected. 40 oranges, 26 reds, and 26 yellows is what we expected. So let's go, once you have the observed numbers and the expected numbers, let's go to Stat, Goodness of Fit. All right, so not Z, T, or proportion stats, but down here you've got Goodness of Fit test. We're doing a chi-square test. So where do we get the observed data from? How about the observed column? And where do we get the expected data column from? Expected. Now, if one thing you could do is, say M&M's claim that there's an equal percentage of all the colors, right? Then you don't actually have to put in the expected. You could just hit this button that says all cells are in equal proportion. So if M&M's claim that everybody's equally distributed, there's the same percentage for every color, then I would just hit that. I wouldn't actually go through and calculate them. I wanted to, even though I found the expected, I'm just going to go ahead and leave it there. Let me see what it shows me. So That's an interesting deal. Something went wrong here, because look at my expected numbers are exactly the same as the observed. So I think I screwed up here. Observed, go to the observed column. Expected, I guess I accidentally changed that. Go to the expected column. All right, I had that one in the wrong column. Now let's see. Okay, there we go. So again, 5 degrees of freedom. There's the chi-square distribution, pretty close to what we found, but again, we were rounding, and there's our p-value of 13%. All right. So to do this on Statcrunch is pretty simple. Just put in what you observe, what you expect. You go to the chi-squared distribution for goodness of fit, chi-squared. And again, just make sure you correctly tell it which columns to look at for the observed and expected. All right, that is all. Turn this thing off.